So I've got the Mavilor 48 volt series motor. If we take a look on their webpage, we can find some documents on these motors. There's some dimensions and some specifications. So these is a new range of motors that's designed for 48 volts. Looking at the Copley, we'll take a look at the AccelNet to go with the 48 volts. We're going to do a can open APV module. The module that we're going to start off with is 15 amps continuous 30 peak. There's another version that's 25 amps continuous 50 peak, but this guy, the higher current models would need to be soldered into the board, so we're just could get the board already soldered, APV-073, but we're just going to use the 1530 amp inside the easy board. It's just a plug-in socket. Keeps things simple. And of course, we have 50 amps continuous version. So if you have like a motor that can do 50 amps, then this would be the drive for it. I know Mavilor has some 50 ampers. But the basic thing here would be a connector kit and the easy board. And you don't need a heat sink with this thing, but there are heat sink options. Actually, the heat plate on the drive, if this surface is mounted to the frame, then all the heat comes out that way. So maybe that's better than the heat sink. There's some good wiring diagrams in here. So normally you would connect earth at the drive, hook up a DC power supply, say the 48 volt supply. This delivers power to the output stage. So, for safety, you could cut this. But there's also a V-Logic or a Keep Alive. This is typically 24 volts. I mean, you could use the same 48 volts, but there's other things in the system that are 24 volt rated, like the brake. So this is how you would wire up a brake. On the module, there's a pin which goes to the mounting board, which has the FET, which controls the current through the brake. For this test, I bypassed that, but you'll need to hook this up in order to not bypass the brake. And then, of course, the shielding, all shields go to earth. And, the frame of the drive should have a path to earth. And the motor case, of course, has a path to earth. And that's enough for the cabling. We're going to talk about the feedback device here is a Hiperface. So this is an absolute encoder. There's some options in CME for selecting the Hiperface and then configuring it based on the number of bits and counts per rev along with the sine cosine. And the critical factor here for wiring, the data comes in on A plus and A minus with respect to signal ground. And then you get sine plus and sine minus. We're showing sine minus connected to ref sine, but it's the wiring diagram is really critical here. Before I show that from the documents, I'll just show that this encoder, this SIC encoder, is a 9 volt or 7 to 12. So a 9 volt regulator is typically used. Greater than 80 milliamp should provide enough. So the grounds are common with the drive, but the power comes from the 24 volt, which then goes through the 24 volt to 9 volt regulator. So just taking a look at the wiring diagram here, the feedback cable has a shield. You must connect the shield to earth at the drive. Do not connect the shield at the motor side. If you have a shield, it must find a path to earth, and Copley recommends connecting it to pin 1 on P1 for frame ground. And of course, you've connected the frame to ground so that we have a path for the shield to Earth. So what we're doing here, rather than say sine plus, we're changing the name to sine minus, because actually the sine plus and cosine plus go to reference, and we'll change the nomenclature to minus. This is just to conform to some standard way of wiring up to the Copley, where we say sine plus, sine minus, cosine minus. If we don't wire it up properly, the sine cosine goes one way while the absolute goes the other, and we get a disagreement in the encoder. So that's just a wiring note here. And then this is the regulator chip that we used. It's pretty small. It takes 24 volts in. Outputs 9 volt. So that's 500 milliamps at 9 volt. That's plenty of juice. We've seen this used in several instances of Hiperface with Wittenstein and now Mavilor. So that's a good recommendation. Just to show you the basic setup here. So we've got the motor, we've got the power and the feedback. There's some plate data on the side. I've got 24 volts hooked up to the brake. So we're bypassing the brake at the moment. That could be wired to the brake output to turn it off and on from the drive, but I need to be able to turn the shaft when the power's off, so I'm going to hook up the 24 volts to the brake. You can see the motor power wire is hooked up to the screw terminals with earth here. The heat plate would be mounted to the frame, which would be earth. I've got the 48 volt bus. That's the 48 volt high voltage to drive the output stage. And I've got the 24 volt V logic, again, for the brake and the V logic, and also for this regulator here. So we put the regulator inside of the cable. That's typical for most manufactured systems. So this little regulator fits inside the heat shrink and gets 24 volts and outputs 9 volts with respect to ground. So we've got CME2 downloaded from the web page, up and running, connected to the drive. So the first thing we'll do is the setup screen. It's a brushless rotary with a brake. It's a Hiperface feedback device. It's really 18 bits, single turn, but it has 4096 counts. The interpolation is done once to 4096. We don't want to ignore the feedback. There's some brake stop times configured. We're in a CAN mode, and we're emulating feedback out. So we're going to start by gathering some data. So there's a model number on the faceplate. It's an 8-pole motor. The inertia is 0.074 E minus 3, or 0.74 kilograms centimeters squared. There's some peak and continuous torque ratings. There's a maximum velocity. We got a torque constant in Newton meters per amp RMS on the label there, and a volts per radians per second, and it's 0.08, which translates into 8.3 volts per kRPM. So if you have a 48 volt supply and you divide it by 8.38, your speeds will be less than 5.7 kRPM. Actually, maybe less, because there's some resistance, and at 15 amps, you're going to get some voltage drop. But anyways, if you enter the good data, you can hit calculate, you get initial tuning parameters. That's all good. And then you go tools, manual phase, and we should be able to phase the motor. There's a little bit of poor phasing here, so I'm going to start off with 0. Okay, so it looks like about 60 degrees of offset here. So there's a slight lag as I rotate. That's normal. and then go the other way, slight lag. So this is an open loop micro stepping, and so we're trying to get the right phase of the motor. So if you increase the current a little bit, you can see the phasing looks a little tighter. And this is just open loop, so I don't have the load connected. And so the phase is optimal. Just wire in the logical manner and follow the wiring diagram and you'll be fine. Okay, so this file that we save at the end of the day will be fine. These values are calculated for the current loop, and based on some math model, the software develops some gains, but we're going to have to tune those. Let's start off by tuning the current loop. So I plot auto setup checkbox, apply to the current. It displays what we want to look at. There's a perfect command, and there's the actual. If the gain's too high, you're going to get ringing. When you see some overshoot, cut it in half, and then you should get away from the overshoot. There's a little glitch there, but that's okay. And go for the integral. You know, when the integral is too high, I'll just show too high. That's a wicked integral windup. So we'll cut it in half. There's still a little bit of integral windup. I'm going to cut it in half again. And that looks pretty good. I could maybe use a little bit more, but we'll just check the bandwidth here. I'd like about 1 kilohertz of current loop bandwidth. All right, so yeah, maybe a little bit more. We'll go with the 60 on that. And then I'm going to tune up the velocity loop. And again, we got some default values here. That's a little excessive for Excel. So that's a little nicer. Yeah, these are calculated gains here. If the gain's too high, you should see some overshoot. And so this is sounding a little bit ringy here. So I'll come back and lower that. Yeah, so, you know, cut it in half. And if it's still too much, cut it in half again. I'm going to give it a little bit more integral. And if the integral is too high, then you get integral windup. I always come back and adjust that after I do the position loop. So for the position loop, 4096, and that should be 1 rev of the motor. And again, auto setup checkbox. And this will be 10 revs of the motor. If the inertia is greater than 1:1, you might turn the PP term down a little bit, but I've got no load here, so that's pretty good tuning. Current, actual current, okay. So yeah, maybe, you know, we could tweak the tuning a little bit, maybe throw in some S-curve, affect the trajectory values, maybe round it off a little bit. Okay, so normally the default homing configuration is set current position as home. That doesn't do anything until we initiate homing, and you can see here on the control panel that the homing is not referenced. And also, you know, this encoder is absolute, so in this position it came up like I'd have to turn it by hand to get to 0. But what if I want this like straight up and down position to be 0? Well, then I'll need to read this position and subtract that as a -662, and then change this homing method to absolute immediate home. I can save that. I could issue the homing and it'll take where I'm at and subtract 62 from it. And then if you reset the drive, the drive will come up in this position at 0 or some other position, and then you'll be at